Assalamu alaikum. Today we will be discussing about electric dipole in an electric field. Before starting this article, one should know what a dipole is. So, to define dipole, referring back to chapter number 23rd, we have discussed dipole over there as well, but I'll repeat the definition again. An electric dipole is when we have two charges of same magnitude but opposite polarity and separated by a small distance, it is known as dipole. So इधर हम देख सकते हैं कि I have a negative charge and I have a positive charge. कोई भी डिस्टेंस इसका नाम दे दिया है 2a. 2a इसलिए नाम दिया गया क्योंकि बुक में ये इस्तेमाल हो रहा है. So let's call it 2a. So it has been separated by a distance 2a, and this is a very small distance. So I say that I have created a dipole over here. So dipole is when two charges of same magnitude but opposite polarity are separated by a very small distance, is known as a dipole. So इस dipole को अब हमने किसी भी इलेक्ट्रिक फील्ड के अंदर रखना है और इस इलेक्ट्रिक फील्ड का इफेक्ट इस डायपोल के ऊपर जो है वो हम स्टडी करना चाहेंगे. एक और जो टर्म हम इसमें यूज़ करेंगे दैट विल बी इलेक्ट्रिक डायपोल मोमेंट. इलेक्ट्रिक डायपोल मोमेंट जो है उसको डिफाइन इस तरह से किया जाता है कि द इलेक्ट्रिक डायपोल मोमेंट इज़ द मेजर ऑफ सेपरेशन. इट इज़ द मेजर ऑफ सेपरेशन, दैट इज़ ये इनके बीच में कितना डिस्टेंस है of positive and negative electric charges within a system. So इनके बीच में जो टोटल डिस्टेंस आ रहा है, जो गैप है, उसके जो जब हम मेजर करते हैं तो दैट इज़ नोन एज इलेक्ट्रिक डायपोल मोमेंट. इलेक्ट्रिक डायपोल मोमेंट को मैथमेटिकली हम रिप्रेजेंट करते हैं. P is defined as, these three lines represent defined as, P is defined as 2a into Q, as Q is the magnitude of the charges. So Q जो है हम उसको जो डिस्टेंस आ रहा है उसके साथ मल्टीप्लाई कर देंगे. This electric dipole moment, it's a vector quantity. So when I want to represent it as a vector, so this electric dipole moment will be written as 2a. A is basically a vector over here, and the direction of the vector is from negative to positive charge. So इसकी डायरेक्शन जो है वो नेगेटिव से पॉजिटिव चार्ज की तरफ होगी. ये इसमें इस फिगर में ये बताया भी गया है कि P की डायरेक्शन जो है वो फ्रॉम नेगेटिव टू पॉजिटिव चार्ज आ रही है. So it's a vector quantity, it depends upon its direction and it must have a magnitude. So इलेक्ट्रिक डायपोल मोमेंट भी हम इस आर्टिकल में इस्तेमाल करेंगे और उसकी डेफिनेशन जो है it is the measure of the separation between the positive and the negative charge. So now coming to the article that is that is electric dipole in an electric field. So what happens when I place this electric dipole in this electric field? When I place this electric dipole in this field, this field is external to the field which is already existing because of these two charges. So obviously when we have a charge, उसकी अपनी कोई ना कोई फील्ड तो होती है, लेकिन हम उस फील्ड को इस वक्त नहीं कंसिडर करेंगे. We will consider the effect of this external field which affects this dipole which we are going to place in this field. The field is uniform. So the field I have introduced over here, it's a uniform electric field. Ignore the lines because lines के बीच में gap जो है वो इतना uniform दिख नहीं रहा, लेकिन we are considering a uniform electric field over here. And again I have placed this dipole over here, and the direction of the dipole is from negative to positive. When I place this dipole in this electric field, obviously it will try to move this dipole according to the direction. So the force on positive charge will be in the direction will be towards the right side, and the force on the negative charge will be towards left side. इस फिगर में ये एंगल एक नज़र आ रहा है, ये वो एंगल है जो ये डाइपोल इस फील्ड के अंदर अगर इस पोजीशन में पड़ा हुआ है. सपोज वी कंसिडर scenario when the dipole is placed at this position making an angle theta with the electric field. So इसमें क्या होगा कि the force is equal to QE. Obviously we are talking about electric force over here, so the force will be QE over here, and uh, and as I have told you that these two charges are same in magnitude but opposite in direction, so some of the forces that are acting on these charges will give me a zero. So I'll get zero force, sum of total force will be zero. अब ये होगा ये क्योंकि दोनों के दोनों जो हैं वो ऑपोजिट चार्जेस हैं, तो एक फोर्स अगर राइट साइड पे जा रही है और दूसरी लेफ़्ट साइड पे जा रही है, तो दोनों का इफ़ेक्ट ये होगा कि वो इस डाइपोल को मूव करना शुरू कर देंगे और इसमें एक टर्निंग इफ़ेक्ट प्रोड्यूस करेंगे. इफ़ यू रिमेंबर, द टर्निंग इफ़ेक्ट इज़ नोन एज टॉ. और टॉ जो है जब भी किसी बॉडी में प्रोड्यूस होता है तो हम कहते हैं कि बॉडी जो है वो अब रोटेट करना शुरू हो रही है. और टॉ जो है इट डिपेंड्स अपॉन दीज टू वेक्टर क्वांटिटीज, दैट इज एफ द फोर्स and r the moment arm. So tau is represented by this symbol where f is the force and r is the moment arm over here. As tau is also a vector quantity, so we'll take cross product between these two vectors. So the cross product between these two vectors give me fr sine of theta if I want to know the magnitude of this tau. So I'll simply cross product को जब हम simplified form में लिखते हैं तो that is fr sine of theta. So यहाँ पे we know that our f is QE and R is A. So when I write the tau produced in positive charge, so I can write tau is equal to QE A sine of theta, and when the same tau is produced in the negative charge, I will write again the same equation will be written, that is QE A sine of theta. So total tau produced in the dipole will be sum of these two taus, and total tau will be equal to QE A sine of theta plus QE A sine of theta, that is the one produced in positive charge and the other one produced in the negative charge. So sum of these taus will give me 2 QE A sine of theta. And if I go back to the definition of the electric dipole moment, there I have defined that P is equal to 2AQ. So I can replace this 2, this Q and this A with a P, and I'll get tau is equal to PE sine of theta. And when I want to write it in the form of vector, I'll simply write P cross E. This P is the electric dipole moment and this E is the electric field. So the tau produced in the dipole present in an external field will be P cross E. Now, if we want to calculate the potential energy of the system, when I say system, it means that the dipole which is present in the electric field, I want to calculate the potential energy for it. The work must be done by an external agent to rotate the dipole through an angle theta, so that the dipole moment vector P is less aligned with the field. So when I if I want to rotate the dipole, when the dipole is in this position and the electric field is in this position, they are not aligned to one another. As I turn this dipole in this direction and this goes over here, so if I change the theta over here, the dipole it will move towards more aligned position with the electric field over here. But if I move this dipole in the in this direction, then the dipole will reach this position, and when the dipole is in this position, I'll say that my dipole is not aligned with the electric field. So now I want to calculate the potential energy stored in the dipole. I know that work done is equal to tau d theta, where my tau is Pe sine of theta, and I have this change in theta. So as I'm varying the position by varying the angle of the dipole, I am storing potential energy within the system. So I can write this potential energy. This is actually the work done, and I have told you before that in most of the problems in electricity, the work done is given by U. So now if I want to calculate the potential energy, I can write UF minus UI equals to integral tau d theta, where I can take this tau outside, and my change in potential energy will depend wholly solely on this change in theta. So if I use the formula for tau, I know that P E sine of theta, because I have defined my tau as P cross E, and this P cross E, when is written in simplified form, I have this P E and sine of theta, sine of theta. So I can write P and E outside the integral, and we'll solve this sine of theta to get my solution. So I know that integral of sine of theta is minus cos of theta. I'll apply the limit, and by applying the limit, I get PE minus cos of theta f minus into minus cos of theta I. By simplifying it, I can write it as PE cos of theta I minus cos of theta f. So now simply by giving the value to theta, if I say that my initial theta is 90, the position where the dipole is totally misaligned with the electric field applied, so I give the initial point to be 90 degrees, and at some a final point, that is theta. So I can simply say that my UI will become 0, because I know that my cos of 90 will be 0, and I get this theta f can be replaced by this simple theta over here, which I have given the value. So I can write this VF UF, sorry, equals to U, which is equal to minus PE cos of theta. So from here I can see that my potential energy is equals to minus P dot E. We know that when we have a dot product, and this dot product will always give me a scalar quantity, and I also know that my potential energy is a scalar quantity, and this proves here that the dot product between these two vectors again will give me a scalar quantity in the form of the potential energy stored in the dipole moment, which is present in an external electric field. Now we will discuss some problems related to the article. In the book we have example 26.8. The statement says the water molecule has an electric dipole moment of 6.3 into 10 raised to minus 30 coulombs meter. A sample contains 10 raised to the power 21 water molecules with the dipole moments all oriented in the direction of an electric field of magnitude 2.5 into 10 to the power 5 Newton per Coulomb. How much work is required to rotate the dipoles from this orientation, that is theta equals to 0 degrees to 1, in which all the moments are perpendicular to the field, that is theta is equal to 90 degree. Uh, so P is given, E is given, number of molecules they are given, and theta is given, initial theta as well as final theta. These two are given over here. So given data is P 6.3 into 10 to the power minus 30 coulombs meter, number of molecules 10 raised to the power 21, electric field 2.5 into 10 to the power 5 Newton per Coulomb, and initial theta 0 and final theta 90 degrees. These are the things which are given in the problem. Now we want to calculate the work done. So for that, first we will simply try to find the difference in the potential energies as we have calculated in the article. So UF minus UI, the final theta is 90 over here and the initial theta is 0 degrees. So simply I'll put in the values, that is PE cos of 90 minus into minus PE cos of 0. So this, it will get cancelled because cos of 90 is 0, and I'll get PE cos of 0 minus and minus, it will give me a positive sign. So cos of 0 is 1. So simply I will multiply this P with this E and I'll get the work done. Now the total work done, because of 10 raised to the power 21 molecules present, so I will simply multiply this with the number of molecules and I'll get the work done within the system. So this is a simple problem in which we come to know that if we want to calculate the work done, we simply use this formula, and if a certain number of molecules are present, so the total work, it depends upon the number of molecules. So we will multiply the number of molecules with this calculated work done over here. Now I'll be solving another problem. This one is given in the exercise. The problem says a small rigid object carries positive and negative 3.5 nanocoulombs charge, which means that I have 3.5 nanocoulombs charge, that is the magnitude of the charge is same, and positive and negative defines that, oh, okay, we are having a dipole over here. So it is oriented so that the positive charge has coordinate this. The positive charge is lying at this position and the negative charge is lying on this position. Now first we have to find the electric dipole moment of the object, that is, first of all I have to find P, and in the second part, whereas in the A part they have also given me this electric field, in B part we have to find the torque acting on the object. In the C part, find the potential energy of the object field system when the object is in this orientation. And in the last part, if the orientation of the object can change, find the difference between the maximum and the minimum potential energy. So first of all, I'll write down the data for part A, and it is the coordinates of positive charge and negative charge. If I imagine that I have a graph paper and consider some origin over here, so according to that, if I draw this minus 1.2 and 1.10, so the positive charge lies somewhere over here and the negative charge lies somewhere over here. So and I draw the separation between them, and now I have a dipole over here. So the magnitude of the charge it's given, that is 3.5 nanocoulombs. I have to find P, that is the electric dipole moment, and E is given. So and it will be a simple formula, that is I know that electric dipole moment is equal to 2aq, and whereas 2a, that is the separation between these two charges, can be calculated by using the coordinates already given. I have the coordinates of my positive charge, and I have the coordinates of my negative charge. Simply subtract them and I'll get my 2a, where the distance between these two charges. So the distance between them is minus 2.6 I plus 2.4 unit vector j multiplied by 10 raised to the power minus 3 meters. They were given in millimeters, so I can convert this milli into 10 to the power minus 3 and meters. So now I have 2a. I know the value of q. Simply I multiply these and I get the value this. So it is a simple calculation. You simply have to put in the values and you get the answer over here. There is a little mistake over here. I have written this 2, which should not be written over here, because I have already calculated 2a over here. So when I have calculated 2 over here, then there is no need to write this 2. And when I multiply this 3.5 into 2.6, I'll get 9.1. And when I multiply this 3.5 with 2.4, so I'll get this 8.4 unit vector j into 10 to the power minus 12 coulombs meter. So please correct this. This is I should not have written this 2 over here. Okay, now proceeding to part B. In part B, I have to find the tau. I know that tau is equal to P cross E. I know the value of P now. I know the value of E. It is given in the data. So simply I'll take the cross product between these two. I cross I, if you remember the rules, that is I cross I is equals to 0, and so I cross I will give me 0, but I cross j will give me a unit vector k over here. So when I multiply this with this, I get 44.6 unit vector k, because I am taking, this is the cross product, it is not a simple multiplication sign, so it's a cross product. And when I take j cross I, this will give me minus k. So 8.4 and 7.80, and I take a cross product between j and I, it will give me unit vector k but with a negative sign, and j cross j will give me 0. So after simplifying this, I get 44.6 unit vector k minus 65.5 unit vector k into 10 to the power minus 9 Newton meter. So subtracting this 65 from this 44, I get 2.09 into 10 to the power minus 8 unit vector k Newton meter. So this is very important that you write this unit vector, and there should be uh, a bar on the top of this tau, because I'm not talking about the magnitude right now, I am talking about this tau vector. So when I have written this unit vector k, then this tau must have a bar over it, or must be written in bold form. So the tau vector is equal to minus 2.09 into 10 to the power minus 8 unit vector k Newton meter. In the C part, I want to find the energy. So to find the energy, we have calculated the formula that we have known this, that is U is equal to minus P dot E. And now I'll be taking the dot product. In the dot product, I know that I dot I and J dot J will give me 1, and I dot J and J dot I will give me 0. So when I multiply this with this, I'll get this 71, and when I get multiply this with 4.9, I get 41.2. And overall, this whole thing is being multiplied with this negative sign over here. So this will become positive, and again this will become positive, because both of these have a negative sign, and overall the equation becomes a positive value, and I get this U equals to 112 nanojoules. So now the energy is 112 nanojoules. In the D part, I want to find the difference, that is the difference between the maximum and the minimum energy which have been stored. So for that, I simply take the magnitude of P and magnitude of E, and by doing that, the magnitude of P is equal to 12.4 into 10 to the power minus 12, and magnitude of E is 9.21 into 10 to the power 3 Newton per Coulomb. And I know that my maximum energy is PE, which is equal to 12.4 into 10 to the power minus 12 into the electric, the magnitude of electric field. So I'll get 114 nanojoules, and the minimum will be with the negative sign, because if I look at the angle, so the maximum value within the angles, I can have a +1, and the minimum value can be -1. So the maximum value will be 114 nanojoules, and the minimum value will be -114 nanojoules. And when I use this, I simply have to subtract the maximum from the minimum, and I have this value. Subtracting this from -114, minus minus will give me plus, and what I'll get is 228 nanojoules. So these are the two problems which are related to the articles which we have already discussed, and I hope that now the things are clear to you, that when we have a dipole present in an external field, what will happen to it? It can rotate. Tau, your turning effect will be produced in it. So if it is totally misaligned, and I'll change the theta, it will move towards the aligning itself with the electric field. Or if we want to misalign the dipole, we can increase the theta from the line position, and by doing that I can place my dipole in the misaligned position in an external electric field.